Good morning, everybody.
How are things?
Oh, they're doing good. I've got my cup of coffee, so I'm happy. Big cup of coffee too. All right. Okay. Let's see what we got on the box for today. Shit, where did chat go? All right, so let's. It's funny, Paul, your name always comes up front and center in my screen for some reason. I don't know why. Always find that kind of funny.
I don't know if I should find that concerning or not.
Let's see. All right, so does anybody
on mic now?
Say what again?
We on mic now?
You can be. If you want, yeah. The only thing is if you have a lot of background noise, to mute your mic just so it doesn't disturb other people. But you're more than welcome to have it on and then just shout out questions as they come up. I think that will work pretty well. Kind of as you would in class, really, to be honest.
Okie dokie.
So, quick question to everybody. Have you had a chance to look at the Mars PowerPoint yet? Anybody?
No.
I've got it on my phone.
You got it on your phone? That would be interesting. All right, so I know I put it out. Go on.
No, I mean, like, I don't have a laptop, so like my phone is my laptop. You know what I mean?
Oh, okay. That's gonna be interesting. If there's any way you can borrow one, ask around because it will make doing the exam a lot easier. Also, I've heard reports of people that do online exams. Phones seem to be a little bit less stable for some reason, in terms of I
have like a desktop.
Oh, okay, right.
For computer stuffs.
Yeah, I think that would, if you can, that would be wise. Where's chat gone? Come on, you pest. Sorry, trying to get there. There we go. Word of the morning today. Well, we've had. Oh, sorry, Maria. Can you hear me now? Anybody? This is just going through questions on chat. Oh, okay, awesome. Cool. Hopefully that's the same for Angela too. All right, let's stick that over there. So it's not a word, it's a phrase. Shoot, how do you spell the last bit of that word? There you go. There you go. That's the phrase for the day, because it's super cool. Basically evidence potentially that there is water on Mars. Okay, so where possible, try and go over the PowerPoint beforehand. You get my dulcet tones as an accompaniment as well. Because, hey, get off of that. It just gives you the ability to ask kind of more directed questions during this session, right? Because this is unfortunately the main time in which you have me to yourselves, right? So where we can have this back and forth. And so if you can go through the PowerPoints and the audio ahead of time, that kind of gives you a kind of head start essentially. Right, I think it'll really help people, to be honest, because there's going to be a lot of stuff kind of coming through, right? There's a also as we're kind of getting caught up with the class too. and it also frees me up a little bit to expound on certain points more rather than covering the whole material. Yeah, so if you can do that, I think you'll gain a lot more out of it than just listen to me chunter on a webcam. Anyway, so let's just see, who do we have here today? Still working my way. We've got quite a few people here today. That's awesome. Well, glad to see everybody. Hopefully you're all staying safe and sound and not going completely nuts in your homes. Things like that. Anyway, so the big point about Mars really is it's a bookend. Pardon me. So if you think of, Earth is bang in the middle of this habitable zone around our star, then Venus and Mars are kind of the bookends on either end of that, right? So Venus is a lot closer into the sun, and it has a much thicker carbon dioxide rich atmosphere, so it's a lot hotter, right? So what's that, 460 Celsius, give or take, compared with 14 here, right, on average surface temperature on Earth. Now, if you go the other way and you go to Mars, you've got the opposite. Now, partly that's because Mars is further away from the sun than we are. So if you remember how insolation reduces as a square of distance, I think. Yeah, it's a square of distance, that's right. Then, Mars is about 50% further away from the sun than we are, about 1.5 AU. So it's going to receive whatever the square of that is, less sun. But the other reason as well that Mars is a lot cooler and drier is because it's smaller. Right, so if you look at this slide, can you all see the PowerPoint that I'm going through? Anybody? Yes? No?
Yes.
Oh, okay.
No,
You can't?
kind
You're
of.
on Earth and Mars, right? Like a comparative view.
Yeah, that's right.
Yeah.
Okay, so you can see here, like, if you remember Venus was around the same size as Earth, a little bit smaller. Mars is much, much smaller, right? So that has several consequences, right? One, it has less gravitational potential energy in the first place, right? There's less mass that's kind of coming together and differentiating to then give off heat later, right? That whole virial theorem, right? So it has an awful lot less volume to generate heat from the process of accretion. It also has less gravity, right? So they're equivalent in terms of composition, right? They're both rocky, semi-metallic terrestrial balls, right? And so they're approximately the same density, so they have a lot less. Mars has a lot less gravity, so it's much less able to hold on to an atmosphere, right? And so the atmosphere on Mars is about 1/100th of the density of the atmosphere on Earth, right? And if you remember about Venus, pressure of the atmosphere on Venus at ground level is about 100 times that of Earth, right? So there's a kind of a log 100 like change essentially through the solar system from Venus, which has about 100 atmospheres, Earth, which by definition, has 1 atmosphere, and Mars, which has about 1/100th of an atmosphere, right, in terms of density. Still has an atmosphere, right? It still, goes out, I don't know how high the troposphere on Mars is, but it's still, it's still a decent sized atmosphere. It's just a lot less dense, right? And so what that means is that A, it has less intrinsic energy, I guess, and B, it has such a thin atmosphere that it doesn't retain a lot of the reduced solar energy that hits it, right, compared with Earth. So Mars is a lot colder. On the flip side, it's actually tilted, right? So remember I was saying that Earth is like, it's kind of about like that, give or take. And so it rotates around a tilted axis, right? It's about 23.5 degrees. Venus is like that. So it gets nice and slowly baked as it slowly rotates around its axis as it goes around the sun. Mars is a lot more like Earth, right? It's tilted like that. So there are seasons on Mars, which we'll get to later. And also, that tilt is very similar to Earth's. It's 25 degrees, I think. Earth's is 23 and something. And so it has that same kind of change of seasons that Earth does. It also rotates at about the same rate around its axis as Earth does. Not exactly the same. So Martian days are called sols, S-O-L. And there are, what's the orbital period of Mars? It's like 680 Earth days or something like that. And a few, I think it's slightly fewer rotations than the Earth would do in the same amount of time. So like 660 sols, or the other way around, I can't remember. They're very similar. So in terms of its characteristics as a planet, it's very similar to Earth, but it's so much smaller and further away that it's a lot cooler and has a much thinner atmosphere. So that's what really drives a lot of Mars's properties. Also, it's another example of how volatiles change over distance in the solar system, right? So if you remember, on Venus, there's no liquid water, very little atmospheric water actually, and a huge amount of carbon dioxide, right? But it's all as a gas. On Earth, we've got carbon dioxide, less so, but a lot of water in a liquid state. And if you go further out to Mars, Mars has frozen water, we think, because we can't see it directly, we can see it underground. But it also has a carbon dioxide atmosphere, but it has carbon dioxide ice caps. So if you look at this picture of Mars, which is in true color, right? So it is a red planet, right? From iron oxides mostly. You can see those white bits at the top and the bottom. Those are carbon dioxide ice, right? So that gives you an idea of how much cooler it is relative to Earth, relative to Venus, right? That kind of, you know, basically what we're talking about in terms of frost line and stuff like that, right? So Mars is kind of getting towards the edge of the frost line, to be honest. Okay, so one thing that's kind of neat as well, so you can see here the axial tilt of Mars, and just from this, my guess would be that the sun is to the left, right? And the reason why I can guess that, and it is just a guess, I don't know whether it's true or not, is that you can see that the southern polar ice cap is much more defined, right? So essentially, this area down here, this is winter in Mars. This area up here, that polar ice cap sublimates, so it turns back into gas. And essentially, there's a convection around Mars where that carbon dioxide then freezes on the cold pole. And then, obviously, when the rotation is, the planet rotates the other way as it's going around the sun, then this pole would sublimate and go to the north. Right, so you can actually look at the weather over time, and there's also a probe around. This was, I think, this was part of the Curiosity mission, which is still trundling around on Mars. But there's a satellite going around, scooching around Mars, called the Mars Reconnaissance Orbiter. It's Orbiter? Yeah, I think so. And that's actually been able to observe Mars over the course of several Martian years, right? So it can actually observe these changes in weather and seasons, and a much more thorough snapshot than something just going shrink past as probes do, right? So we know an awful lot about Mars. It is by far the most well explored environment outside of Earth. Also, because of that MRO, that satellite, we're able to find the scattered remnants of the Indian Martian lander, which crashed, I think, last year, within a matter of days. We just kind of scanned where it should have landed, and they found like this little reflective dots, basically equals bits of lander. So it's kind of interesting. We're able to find stuff on Mars, way faster than we can find stuff on Earth, for example, which is pretty cool. I'm not going to go into the history in too much detail because I went over that in the audio. There's some fun stuff in there. But essentially, in terms of exploration, about 2/3 of the things we fire at Mars get there, or at least the 2/3 of the things that we try and land on Mars do so in a way that means they still function afterwards, right? Because everything's landed on Mars. Just some bits land in one piece and other bits land in lots of pieces, right? And I think, where's the Beagle? I'm just trying to, there it is, Beagle 2. Pretty sure that was a European Space Agency one. That was a huge screw up. That was basically a collaborative effort where they forgot that Europeans used different units from Americans, or something silly like that. And so, parts of the bits didn't fit and it fell apart as it was landing. The big issue with landing stuff on Mars is its atmosphere, right? Its atmosphere is so thin that, on Earth, it's quite, we have parachutes, right? So land, get something through the atmosphere at an angle that means it doesn't burn up, and it just floats down to the surface, super simple. You can't do that on Mars, at least not very easily. Most of them have like some kind of huge parachutes to try and slow them down a little bit. So obviously they're going pretty quick when they get there. And the smaller stuff, typically what they do is they surround it with enormous inflatable balloons. So basically it lands on Mars like a piece of giant popcorn, and it just kind of rolls around for a while until it comes to a standstill, and then those bags deflate and little rover kind of wanders out. Doesn't work for the big stuff, right? Because there's simply too much mass. So Curiosity was actually a super cool, is this a picture? No, this is by Opportunity. Curiosity is huge. It's actually nuclear powered, right? Not in the conventional sense, but by radioactive decay. And it was the first ever landing by what's called a skyhook. So you can tell I'm kind of nerding out a little bit about this. But essentially the idea behind getting Curiosity down is that it kind of slowed down to a reasonable descent rate, the lander, and then Curiosity was kind of underneath it like so. Then it used retrograde boosters like so to kind of slow it down further, and then it hovers like so above the surface, and Curiosity went down on a rope till it got to the surface, and then it drove off. Super cool. And essentially that was a trial of the technology that's going to be used for the Mars, well, it was 2020 rover, but now it's going to be 2021 rover. So yeah, super cool stuff. And as you can imagine, there's, I think, 2 hours time delay in radio transmissions from Mars to Earth because of the distance. And so you can imagine that the flight crew for the Curiosity mission kind of probably shitting bricks, for a couple of hours until they found out whether or not this thing worked. Anyway, I think that's really cool. So this is, and if you go to just type in NASA and Mars rovers pictures, there are literally hundreds of just stunning pictures of Mars, right? Absolutely just eerie, really, I would say, because it's not an alien planet, right? But it's not our planet. It's somewhere completely else. And so this is a cool picture that Opportunity took. You can see its tracks. I don't know if it was doing like a burnout or something like that. Go woohoo, like a kind of rodeo cowboy or something. I'm not sure. But anyway, it trundled around a lot. It was on Mars, wandering around for 14 years. And covered 25 miles, right? So it might not sound like much in 25 years, but these things don't move very fast. They've got really small wheels. And also they're not autonomous. So mission control goes, go this direction for 300 feet. 2 hours later, that signal gets to Mars, it moves. Then they wait 2 hours after that to see where it ended up, and then they can send it a new one. So it's like kind of, yeah, driving by email almost, right? Well, you can also see here the downfall of Opportunity, right? So Opportunity was solar powered. You can see these huge solar arrays, which powered its instruments and its motors. And basically it got hit by a huge dust storm. Hello.
How big are the rovers?
Let's see. You don't need to see that. Just give Paul a nice fright with all my tabs.
Why do you keep so many tabs open at once?
Oh, because I've got lots of different things going on, basically. So I got some news, got some forums, got some work, got some pictures. Come on. Let's see if we can get this as a bigger picture. No, really, I want to see this picture. Anyway, there we go. My internet's a little slow right now. So that there is, I think that's Spirit, which is one of the smaller, one of the current generation of rovers, right? So Spirit, Opportunity went down together in 2004. Yeah, around then. Curiosity was bigger than that, so not hugely bigger than that, but probably about 20%. So it's a size of like a Yaris, basically. One, or Mazda 2, one of those small compact hatches that you see driving around, rarely in Texas. So we're not up to the size of a, F450 Julie yet, with coal stacks and stuff. Anyway, so they're pretty huge, right? If you think about it in terms of lifting that stuff up out of Earth orbit, right? They are pretty massive, right? And so the Mars 2020 was going to go on the latest generation of NASA boosters, which is pretty huge. Let's see if I can get this back over there. Ah, good choice, Vivian. I'm going to do the same. Anyway, so one of the curiosities about Mars is that it has planet-wide dust storms. So it doesn't have a super thick atmosphere, but it has enough of an atmosphere that these dust storms can rage for weeks, right? And cover enormous parts of the planet at the same time. They kind of feed on each other because they increase thermal retention, right? So more of the sun's energy stays there, and that drives the wind currents, and it's kind of like a positive feedback, basically. And that's what covered Opportunity, and it basically died, which is very sad, because its panels got covered with dust, and it, couldn't do anything more. So kind of sad, actually. I think the people that, you know, you can imagine that there were people who had been working on that mission for 20 years, and they're just saying opportunity, and nothing comes back, you know, for a couple of years. Anyway, what's next? Oh yeah, so this is Curiosity. Curiosity is actually even more awesome than those other two. So it has a drill on board and ability to kind of drill into the surface of Mars, down into the bedrock, and actually suck up material and analyze it in a gas spectrophotometer. So it can really look for basically organic molecules, signs of life, right? That's it's not able to definitively say that those molecules are the result of life, but it's certainly looking for those biosignatures. Okay, so I've got unlimited time today. Hey, so we're not going to get cut off like last time, which was super annoying. But anyway, I'm going to move on a little bit, right? So talked a bit about this. Basically, one of the reasons we think that Mars doesn't have much water on it is really that that water is stripped from Mars by the solar wind, right? Because it doesn't have the same kind of magnetosphere that the Earth does. So I don't know if you remember from earlier on in the course, we talked about the magnetosphere around the Earth. So essentially you've got Earth like so, and then you've got this magnetic field kind of going into and then out of and around the Earth like so, like a toroid donut, essentially. And that magnetic field protects the Earth from the solar wind, right? And actually ends up as being like a kind of tail. If the sun's over, kind of blowing, solar wind's blowing this way, you get this long tail of charged particles, right? And where that magnetic field goes into the southern pole and the northern pole, those charged particles come a bit closer, and that's what causes the aurora borealis and the aurora australis, right? So the northern and southern lights. Anyway, that essentially protects the Earth's atmosphere from being stripped of a lot of stuff, as well as protecting life on Earth as well. And so Mars isn't large enough, they think, to have a molten rotating core like the Earth does. And as a result, it doesn't really have a magnetosphere. And so they think that over the last 4 billion years or so, even if there was water on Mars, and we're almost positive that there was, that water slowly got kind of blown out of the inner solar system and then ended up as part of, you know, maybe Jupiter or Saturn further out. So essentially our atmosphere and our magnetosphere really saved us an awful lot of strife. That's kind of the counter argument for life being elsewhere, right? There are so many things that worked in favor of life being just right here that
Dr. Cook,
Hello.
Pedro has a question in the chat.
Oh, I'm sorry. Crab sticks. Where's my chat gone? Oh, here we go. Oh, I'm sorry. I didn't have that up. Let me. So it's kind of funny seeing those comments like after the fact. Sorry, let me answer a few of those questions before I go rambling on. Size difference? Not really. I mean, gravity is less on Mars. It's not the same, less as in the moon. I think it's 0.7 of Earth gravity. So, you know, you'd bounce around a little bit. It'll be a lot easier to run, that's for sure. But it doesn't really have any difference on the size or the functionality of the rovers, right? They're designed for that particular environment. Basically, the bigger they are, the more equipment they can carry, right? And that's really why Curiosity is so much more scientifically able than the prior rovers, is simply because it can just carry more stuff. That was to Mariah. It would be very sad to sing a happy birthday to yourself. They probably sang it to it. All right, there we are. Well, Robertson, you may get your wish if you live long enough for Elon Musk to fire you there for, you know, new settler. Surprisingly, actually, a little bit of random kind of tangent. Someone, I don't know who it was, basically was proposing to establish a colony on Mars, which is extraordinarily fraught. It's not a trivial matter. And they got something like 20,000 applicants on the internet. Now, for me, the last thing I'd want to do is spend the rest of my life with a bunch of random ass geeks off the internet. But anyway. So Pedro's question. Couple of questions there. So there are organic chemicals on Mars, without doubt. And Curiosity has found some complex organic molecules. Don't know whether they're caused by life or not, though. So possibly there would be some organic chemicals suitable for life. There certainly would be for chemolithotrophs, without doubt. The promote possible vegetation. Now that's a much more complex question, right? Because vegetation equals higher plants. And have you seen The Martian? Has anybody seen The Martian? Anybody? Hopefully, yes. It's a really cool film. The answer is no. And the reason for that is that there is no soil on Mars, right? The dust, the surface, you know, the kind of like dust and, you know, what we would call soil here, dirt, right? It's not soil. It's called regolith. Let me type that. Oh, that would have been a good word of the day, wouldn't it? There you go, word of the day too. We had phrase of the day.
You're breaking up a lot, Dr. Cook. You sound like Hal from that Space.
Oh.
Nailed it. Space Odyssey.
Cool. I mean, I'd love to do that if I could on purpose.
We don't know what you're saying.
No?
Okay.
Oh, shit.
That's a robot.
Oh, okay. Yeah, I've been getting repeated messages that my internet's unstable. I think the issue, I've actually had this problem for a while. I think it's all the people staying at home and watching Netflix. It's kind of screwing up my internet, basically. Sorry. Would it help if I spoke more slowly? You could lip read.
Kind of.
Okay. I'll do my best. Do my best. Okay, so I'll type out an answer instead. How about that? Right, so essentially soil is rock, dust, things like that. Plus, and this is the important part, so that's, you know, a definition of soil. And, oh, that's because I'm not talking, Mariah. So that's the answer to the organic stuff. God, this is going to take forever if I have to type everything out. Here we go. What else was there? Oh, okay. So is my Wi-Fi is my audio any better yet? Just as a sound check, check.
No, you still sound like a robot.
Oh shit. Let me try because we've got a few different networks here. Let's see if I can. Let's see if this works. I'm not sure whether this will drop or not. That's not very promising. Let's try this one. Tum tum tum. All right, how about now? Is that any better? Anybody?
We don't know what you said. It just and then like anybody, and then that's it. Yeah.
Is that any better? Can you hear me kind of more clearly now?
No, you still sound like a little bit.
You sound like Hal.
Robotic. You sound like he's running out of like juice. They unplugged him. Like I can hear Paul just fine, but I don't know if y'all can hear me fine, but yeah.
Yeah, no, I got you good, man.
I can still hear you all just fine. Well, you just have to take this as being like something amusing, I guess.
So Paul will do the lecture. Is that?
Oh yes, Paul. Could you do the lecture?
That's a terrible idea.
Okay, well, I've been learning American Sign Language.
Amazing idea.
So we could go home and we can run. Oh, anyway, that's about it for American Sign Language for me. Okay, so I'll try and speak more slowly and try and speak more clearly. So hopefully you can understand some of what I'm saying. It may also be the case that Zoom is being heavily loaded. So that's another possibility. If we still have problems, I'll check out WebEx. But personally, I hate WebEx with a passion because I've never found it to work very well. So we'll see. If it continues, I'll check out WebEx instead. So there are really kind of two big things about exploring Mars. One, is there water? Two, was there water, right? It's all about water. And like three, I guess, would be, are there any signs of life? So the Curiosity rover was looking for organic compounds that may have been caused by prior life, but it wasn't really able to determine if those organic compounds were biotic or abiotic, right? But we know an awful lot more about water on Mars than we did. So first up, there is water on Mars. It's just not on the surface of Mars, at least in general. Right? Have to be careful with what I say. So the Mars Reconnaissance Orbiter has a radar, ground-penetrating radar, and it discovered right underneath those polar, quit it. So underneath these polar ice caps on Mars, you also have frozen water. And so that's actually really important for future colonization efforts, because you need water. One, because we need water. Two, there's the hope to turn it into some kind of rocket fuel, like hydrazine or something like that. But in terms of water that was on Mars, right? I'm going to point to something on the screen so that you can see what I'm looking at. This is, I think this is this is Curiosity, because this is in Gale Crater. Mount Sharp, which is in the, so Gale Crater's like that. Mount Sharp is in the middle, and Curiosity is busy kind of going up Mount Sharp, basically. I don't know, for a better view, perhaps. Let's make sure I've got, oh, cool. Does that mean I don't have to speak slowly anymore? Because this is really tough. Let's stick that up there. Yeah, anyway. So if you look here, right, this particular structure here, and I spent some time trying to find a good picture of what I want to show, and there are lots of pictures. So if you look at this, and you kind of imagine that you're in, I don't know, Nevada, New Mexico, somewhere dry and arid, right? This would not be unfamiliar, right? Because this is sedimentary rock. Oh, cool. I'm glad about that. And basically, the only way you get sedimentary rock is if you have water for sediment to fall down and then get compressed into hard layers underneath, right? And there is lots of this on Mars, all over the place, right? So this is a really strong argument for water having been in large volumes on Mars. There's also, let's go here. Sorry, I have to keep going back and forth to get the chat back up so I can keep an eye on that. If I go to the PowerPoint, it disappears, which is kind of annoying. So this is another picture, again in Gale Crater, taken by Curiosity. It's got its little name down there, which is super cute. Again, you go to a Texan river, probably around now actually, maybe in a couple of months, and this is what the bottom of it will look like, right? Essentially, you're going to have a hydrated mud, which then dries out, and then it cracks, right? So these are essentially mud cracks in the bedrock, right? It's not something recent. This is almost certainly like probably 1 billion, 2 billion years ago, right? But this is a really strong argument for water being there. Another one is this. This is a potential landing site for the Mars 2021 rover. And the reason being, this is another crater. So there are tons of craters on Mars, right? Because its atmosphere is so thin, it doesn't slow stuff down much. And also it doesn't have active plate tectonics that we're aware of. And so its surface is pretty old. But anyway, this is called Jezero Crater. And if you were to look at a picture, imagine that this was like a LiDAR picture of, you know, some river estuary somewhere on Earth. You'd be like, oh yeah, look, here's the river on the left, goes through this cut, and then the water fans out, right? It looks exactly as you would expect what's called an alluvial fan on Earth. And if you look at lots of parts of Mars, it looks exactly like terrain, which I've actually flown over a few times on the way to, say, California, right? Parts of New Mexico and it's between Nevada, I think. Can't remember where Arizona is. Maybe Arizona as well. Basically, it looks like it's been cut by water. You know, where you have like something relatively flat, and then you have this cut down through it, and it's full of these kind of channels, basically, which look like they've been cut by water. And there are an awful lot of features on Mars that look just like that, right? So pretty much without a shadow of a doubt, Mars had a lot of water on its surface some time ago. We don't know how long ago. That's what one of the things that this rover is going to try and find out, so we can learn more about the evolution of Mars, essentially. But it did have water. Now the question is, does it have liquid water currently? We know it has frozen water, But what we really care about is liquid water, because that's what you need for life. Yeah, let's have some coffee. Let's check on the chat. Yeah, no one's complaining about audio quality. All I sound like, I'll actually have to look up some, have to watch that film again so I can try and impersonate that just to wind you up. Anyway.
Good movie. Good movie.
Yeah, I've watched it several times, read the book as well. It's pretty cool. Anyway, so the big thing, and this is super, 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 super exciting, right? So remember that Mars Reconnaissance Orbiter I told you about, and the fact that it's observing Mars over its seasons, right? Not just a snapshot as it flies by, but multiple repeat imaging, right? And so it's actually done a fabulous job of imaging in high detail the surface of Mars, way more than we've ever had before. But what it can do is this. It can take pictures like this, right? So you might look at that and go, yeah, bunch of rock, right? Who cares? But what I want to draw your attention to, can you all see me moving the cursor around on the screen? Yeah, these lines here. These lines appear only in summer, and they're pretty sure, briny water. So, and here's another one. This is even clearer here. So if you look at this image, I don't know what this image is showing. It was a relic from a previous presentation. But here you can see it super clearly, right? So all these dark lines, not only do they appear in summer, they disappear in winter. So if you have a volatile compound, such as water, which is normally frozen at a certain temperature and then melts at a higher temperature, and those temperatures exist on Mars. It goes from around 70 Fahrenheit to about minus 195 Fahrenheit. So it goes from pretty pleasant to bloody cold, basically. You would expect that kind of behavior. And so they've been able to observe over multiple seasons, right? Not just one, but multiple seasons. These are called recurring slope linii. So they're basically lines on slopes that happen more than once, is a fancy translation of that fancy phrase. And you can see them here, right? So they kind of dribble down, and then if they either evaporate or they freeze again, and they do this over time. So in that rock somewhere is water, and that water at certain times of the year at least is liquid, right? And that is super, super exciting. That's a kind of, in terms of astrobiology, that's like almost exciting as it gets, short of actually finding life. Okay, so the big question then is, what kind of life might live there? And this is going back to questions Pedro and a couple of others asked about organic stuff and whether it would be able to support life. So not in terms of what we consider plants, but you're telling I'm gonna be liking this subject. Get it? Lichen? Yeah. I'm just going to pretend that you're all laughing at that joke.
Ha 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 ha.
Well, there's at least 2 people fake laughing. That's awesome.
I feel like I'm contractually obligated to boo bad puns, but also you're in charge of my grades, so I'm not going to.
Oh, well, what can you do? Keeps me happy. So anyway, let's see if I can get this down to the bottom again. So the key candidate are organisms called xerophiles, right? So this is adding to your library of phile words, right? We've had thermophiles, we've had barophiles, piezophiles. We'll look at psychrophiles and halophiles later on. But xerophiles are really interesting because they can grow on dry stuff, basically. And Mars is by definition a dry environment which has potentially periodic bits of less than dryness. Essentially, is kind of the best way of describing Mars. And so really, I mean, obviously there's no bread on Mars, right? Because there are no bakers, because there aren't any people. So mold, maybe not, right? But lichen, almost certainly. And lichen is a funky organism because it's a symbiotic relationship between two things. It's a fungi or fungus. I'm a fungi. And there you go. There's another one for you, Paul.
I agree with Angela.
Oh, what's Angela saying about me? Hey, oh. Talk to me like I'm 5 teacher voice. I'll remember that, Angela. Anyway. Oh shit, where was I? Here we go. Back to xerophiles. So it's fungus, sorry, that's rude. Fungus and cyanobacterium. Right, so it's a symbiotic relationship between the two. Basically, the cyanobacteria does the production of energy from photosynthesis, and the lichen provides it with a structured protective space. Right, so it protects it from desiccation, because cyanobacteria are typically marine or aquatic bacteria, generally speaking. And so, you know, obviously they don't like desiccation much, but the fungus around it basically gives it a protective structure that protects it from extreme desiccation and radiation damage, heat shock, things like that. And so this is, you know, a picture of a lichen, right? There are lots of lichens. In fact, Canada is currently trying to figure out what its national lichen should be. And there's this real exciting competition about which is the best Canadian lichen or not. Seriously, I'm not joking, Vivian, look it up. Read about it the other day. Obviously, it's not exercising every Canadian, like about 500 of them. But anyway, and so
it's riveting, totally Canadian.
Yes, exactly. Well, it's very cold and like snowy up there. They don't have much else to do, I guess. So essentially, these things can grow on. I know this isn't a. I'm not sure if this is a linear water activity is a linear scale or not. Basically, nothing can grow when it's down to 0.6, right? And distilled water will be 1, right? So 0.6 is the lowest. 1 is just pure water, and I think we're about 0.95, give or take, right? And most life is around 0.9 to 0.95, and so xerophiles grow at 0.8 or lower. So they are almost certainly require much less water than any other kind of life does. Right? And I think the lowest found is 0.7, 0.75. Anyway, so a great analog, and this is what I'm going to try and do over these lectures, is basically compare the environment on that planet or moon or whatever to one that we find here on Earth, because that's essentially what astrobiologists do. And the best analog of Mars, and you're going to be a little bit surprised by this, is Antarctica. And so you're probably thinking, Antarctica, it's got loads of water everywhere, right? It's just covered in like water stuff, right? Ice and things.
So
but
could there be polar bears on Mars?
There'd have to be seals on Mars first, right? Otherwise the polar bears would go hungry. So probably
Totally.
no. And the seals on Mars be like, where's all the water, man? And they'd be all kind of disappointed if they ended up there, you know, on like a seal or penguin spaceship or something. Anyway, So, and this is again, Vivian, polar bears are in the Arctic. They're not in Antarctica. You're thinking about seals and penguins. Anyway, so a really good analog of Mars is the rockier, kind of less ice-covered parts of Antarctica, such as the one on the left, which is called Victoria Land. And actually, just ever so quickly, this lichen here, which we'll get to in a second, what comes from Victoria Land, right? So it quite happily grows on rocks in Antarctica. And you'll find the same if you go up Everest and find some bare rock. It'll have a lichen on it, without doubt. You know, they're everywhere, right? Anyway, and so the reason Antarctica is such a good analog is it's extraordinarily dry. And you know that whenever you get like very, very cold weather, essentially all of the moisture in the atmosphere freezes, right? Turns into snow and then lands on the ground, turns into ice and snow. So actually there are parts, and this is one of my favorite fun facts, there are parts of Antarctica that are so dry there is no life there, right? These are called dry valleys. They're actually created by what are called adiabatic winds, which is when the air cools down and it kind of rushes down these valleys, right? Kind of gets denser as it cools and then it rushes down to the sea. Let's just double check, make sure. Hang on. I have to keep. Oh, yeah, definitely. So if we put seals on Mars, polar bears will appear. I don't think evolution happens that way, Angela, to be honest. I think it's a little bit more complex than that. I mean, it would be kind of cool, you know, we have to believe. That is true, yes. You never know. Anyway, back onto the program. So Antarctica, actually, the dry valleys, in particular, this is one called McMurdo Dry Valley, the only places on Earth, like the whole of the Earth, that we have not found life. That's it. So you can dig down into the surface here. There's a picture on the right-hand side, and you will not find life. There is no bacteria, no fungi, no nothing living in that. And this is actually a good example of what regolith is, right? So this is not soil. It's not soil because there's no organic matter in it. And in fact, these valleys are so dry that the odd seal or penguin, so here's a seal, right, that wanders in there dies. But because there's no water other than the water that they bring with them essentially in their bodies, these things don't decompose. So there are seal and penguin carcasses in these dry valleys that have been here for probably thousands of years, right? I think that's absolutely astonishing, right? And they essentially are mummified, right? They don't decompose. There's no water. Anyway, and there's nothing around that would colonize them. Get off of that. Come on. They would colonize them and break them down, like fungi or, you know, beetles and worms, things like that. Flies just doesn't exist. So it is a really alien environment, without a doubt. Hey, love, you got coffee in the drip coffee if you want it. Okay. So essentially what they did is they take a lichen from one of these places, you know, scrape off a rock, culture it, and then they wanted to see, can this lichen survive in Martian environments? And the answer is yes, quite happily. Let's just, do we have any, no chats yet. And so they took this lichen and they stuck it in some chambers, and you can see the chamber on the picture on the right. You see that chamber inside that, you know, big box? That's essentially a controlled conditions growth chamber, right? It's a sealed pressure vessel, and those tubes control the gases and the like that go in there. And so basically they reconstituted a Martian environment, as best they can. They can't change the gravity, obviously, but they provided the same gas mixtures, the same temperatures. I think they even provided extra radiation. Uh-oh, internet connection is unstable again. I might have to tell my kids to get off the internet. And did 3 different conditions. One was a control, so that was outside of the chamber. 2 was the equivalent of sitting on the surface of Mars, right? You know, just out in the open. And the 3rd one was equivalent of sitting underneath a like an outcrop or like some kind of protected environment. And the crazy thing was, the one that was living in that protected environment grew perfectly happily under Martian conditions, right? So this lichen almost certainly would be able to grow on Mars. And the even trippier thing, right, and is that part of NASA's job when it creates rovers and things like that is to not transfer things like these lichens to Mars. It's really, really, really important that everything that we send to other planets or moons doesn't contain any life from here that could contaminate that environment unintentionally. And lichens are one of those ones which almost certainly would be able to live on Mars. Okay, so you might think that's kind of cool, right? This is even cooler. Hang on, let's go to the actual picture. So this is another lichen called Xanthoria elegans, and they stuck it on the outside of the space station, right? We're not talking about 75, 85, 95% carbon dioxide, you know, kind of cold. We're talking about the vacuum of space, right? And so all of these, you can actually see there's a couple of astronauts who are doing a spacewalk to just stick it on the side of the space station. And this was, I think this came back a couple of years ago, so it's been a little while since they did this. But if you look in all of these little holes, those are all little samples of, say, regolith or soil or whatever, and lichen. And they're under different conditions. Some of them had filters to kind of mimic the amount of light or type of light that they'd receive on Mars. Some of them were just open to the vacuum of space.
You're kind of low right now.
Oh, crap, am I? I'm sorry. I'll speak more slowly. I was getting a little bit excited there.
Also, there's some big questions in that.
Sorry, I couldn't hear you very clearly. I think you're breaking up on your end as well. You want to write that in the chat if you had a question? Where's my chat gone? No. Zoom is a little clunky. Here we go. We're all breaking up like after high school prom. Cool, lots of sci-fi quotes there. I like the Danger Will Robinson one. Oh, I'm sorry. All right. So I'll speak more slowly. So essentially, they put these samples of lichen on the outside of the International Space Station. Under different conditions, you can see all the different growth chambers on this experiment. But the crazy thing was that after 1.5 years, 18 months, over 2/3 of those lichens were still alive and growing. Isn't that nuts? So essentially, these lichen are able to survive and grow in space. Just think about that. So these are actually a good candidate for panspermia. So potentially life coming from somewhere else. Call it lithopanspermia. And almost certainly, if we wish to colonize Mars and, you know, start terraforming it, lichen would be one of the first, if not the main organism that we use first. Now, obviously, that will take a long time, right? Because, you know, give it a few 100 million years, and they may provide enough nutrients to start making soil and potentially changing the amount of oxygen in the atmosphere on Mars too. Anyway, so given that we're looking for life, we'd almost certainly be looking for life like this on Mars when we go there next, probably in about a year or two's time. So there you go. So they're quite astonishing creatures, and hopefully, if nothing else from this course, you'll get a much broader appreciation of some of the weirder aspects of life on Earth, if nothing else, because some of this stuff is just really, really cool. Does anybody have any questions? You can either shout them out or type them up in chat. I've got the chat up in front of me. Or did that all make perfect sense?
That basically after you were like someone's like on next to something that was like choppy until now when you have given.
Sorry, I'm
sorry.
struggling to hear what you were saying. I think we're having the same problem both ways. Did you say you were unable to understand what I said?
Yes, exactly. I just heard like something about us growing stuff in here, right? And then it was like really choppy. So we had questions, right?
Oh, okay. So I'm going to type this out. So I'll just type this out instead. Trying to think of the can't remember the molecule that gives fungus a lot of its structure off the top of my head. Chitin? Thought that was in insects. Let's see. Oh, it is chitin. You're right. I'm sorry. Glucans, chitin, and mannans. You're bang on there. Now, lignin, Vivian, is more what you find in kind of dead plant cells. That's what makes wood, as far as I can remember. So basically, yeah. Desiccation. Forgive the spelling. Yeah, essentially, if you let's see if I can. See if I find you some good pictures. Okay, so actually you can see in a lot of these different ones, essentially what you have in a lichen is a lot of structure, right? So all of this stuff, these different fungal filaments or whatever is obviously the fungus, and then in that kind of embedded in that structure, oh shoot, I have to remember to speak slowly. In that structure, you'll find the cyanobacterium. And so essentially that cyanobacteria is not exposed to conditions that the outside of the lichen experiences. They're very much protected inside the lichen. You know, some other good pictures. So yeah, lots of different pictures. You can see them here. For example, in this one on the middle left, these are where, I don't know, they say algal. I'm not sure if they're algal or they're definitely cyanobacteria. Perhaps algae is like a, well, that's a protist. Maybe it's protist as well as bacteria. I'm not sure. You can see that here's the layer of that photosynthetic single cellular organism, for want of a better word. And so all of that other structure around it protects it from that harsh environment, yet still allows it to get light to photosynthesize and gas exchange to be able to get carbon dioxide to make glucose, right? And so really that's the, so you know, you have a symbiotic relationship. On the one hand, the algae or cyanobacteria provide the energy. On the other hand, the fungus provides the shelter and the support. And so that's how cyanobacteria, that's how lichen can survive in such harsh environments. Because even while the outside of the lichen might be dying from desiccation or ablation and vacuum or severe cold or whatever, inside, those cyanobacteria are still able to keep doing whatever they're doing. Now, how they can do that in space, I don't know. Most likely they don't grow actively in space, but they're able to survive so that once conditions improve, they can then start growing again. Hopefully that kind of gives you the, and that's like a lot of extreme life, right? It doesn't always grow in the extreme environment. It can more survive it and then continue growing somewhere else. Cool. All right, everybody. It's been lots of fun. Hope you all have a great weekend, and I will see you on Monday.
Have a good weekend.
Quiz on Monday? No.
Have a good weekend, sir.
You too. Yeah. Check the new schedule. It's got an updated quiz schedule in it. Cool. All right. Catch you later, everybody. Where are we at?
Bye.